either this or this, and you can find the other one. So it just turns into an algebra problem. Okay? The difficult thing here is just putting it into your calculator. This is also linked up with this equation right here, the Rydberg equation, when you have the wavelength equals 1 over, let me just remember this, right? 1 over r times 1 over n squared, and that's n squared is going to be the final, minus the 1 over n squared initial. So the n stands for the shell, the energy shell. And this is really when we talk about the Bohr model of the atom. So like n, if we start off an electron that has n equals 6, so it's on the 6th energy shell, and it goes down to n equals 4, well then you put that n equals 6, that's where it starts off. So you put that over there, and this is where it ends up. That's the final. So you put it right there. So with this you can find the wavelength, and I might ask you a question that connects these two equations, because here you notice that we've got the wavelength. You can find the wavelength if you're given these things. If you've got the wavelength, then you can plug this into this equation to find the energy. So you can do this in just 2 steps. Okay? So that's a difficult question I might ask you on the test. Okay. We've done that before. We've done that in tests or quizzes. We've done that in class. Colors, again, we don't need to know the colors. The difference between the models. Okay. We started off when we talked about Thomson's model of the atom. His model of the atom was a plum pudding model. Right? We had little tiny electrons that were embedded in this pudding of positive charge. So here's the little electrons, and here's the positive charge. Okay, it's a loose goose, and it's diffuse. So we've got this positive charge that's spread out. So this is positive, but it's spread. Spread, positive, spread out, positive. So it's kind of like loose and goose and diffuse. So this is all spread out like this. Right? That's the first model of the atom. That's a plum pudding model. But then Rutherford shot some particles. Right? So they turned out to be alpha particles, which are just positively charged helium atoms. And he shot them at these things that he thought were going to go right through. But what happened was that instead, some of them bounced back.
That's what he changed the model, right?
So yeah, so he changed the model. He said, no, you cannot have this all spread out and all loosey-goosey and diffusey. Instead, what's going on is that there's something really massive, something really positive in the middle, and that thing right there, I'm going to name it the nucleus. Okay? And soon after, he discovered it was made up of protons.
Well, that was the same person.
Okay? Yeah, the same guy, Rutherford. And instead of having these electrons sit right there, now he says, oh, you know what they do? They are like the planets, and they just kind of orbit this thing. They're orbiting. Yeah, that's what they're doing. They're orbiting. Like planets around a star. That's what he thought. Okay, so he did the planetary model. Right? Now, we're going to move on from Rutherford. This is Rutherford's planetary model. We're moving on from that, and we're going on to Bohr. Bohr has a different model. His model is
the jumping one.
Yeah. This is the one that, if you look at it, here's the positive, and he's also got the neutrons in there by now, because we have, oops, let's say this is positive, there's the neutrons, but they're very, very small in the middle. And then orbiting down on the outside.
Is the mass of the neutron the same as the proton?
Yeah, basically yes.
Okay.
For our sake, it's really very close.
Okay.
They aren't exactly the same, but they are very, very close. Electrons are really, really, really tiny mass compared to these things right here. So in Bohr's model, he has his electrons existing in these things he calls orbits. But and they are moving around like this in his model, or not in the opposite directions, I guess. They'd be going in the same directions, I think. I'm not quite sure on that. But anyway, here we go. We have the electrons, and they're on the different shells. They don't exist in between. They don't exist there. But they do exist on these orbits right here. And when they move, they get excited. So here, we're going to excite this electron. We're going to excite it with, I don't know, some heat. Okay, we did this in our flame lab. So if you excite this with heat, it goes up to a higher level, higher energy level. You don't see it anywhere in between here. It just goes choo-choo. It just pops in and out of existence. It goes boom, boom, boom. It goes right there. You don't see any. You don't see like a blur of electron going up there. You just go straight up. Now, here is excited, but then when it comes back down, it releases the energy it just absorbed and releases that energy when it comes back down. It releases that energy as radiation, and sometimes it's visible light. Okay? And we can describe this in terms of an equation. So like if n equals 3 here, and this is n equals 2, maybe we have n equals 1 right there. If we go from n equals 3 to n equals 2, then there's some wavelength that's given off. And that equation that we went over earlier with the wavelength equals the 1 over the r times 1 over this one right here, that equation, that describes what's going on here. Okay, the wavelength given off, the wavelength of this visible light is described by this equation. So if you start somewhere, you start there and you end up there, that can tell you what the wavelength's going to be. Right? So that's Bohr's model, and then finally we went on to Schrodinger's model of the atom. And Schrodinger's model of the atom is different because there was a discovery about electrons. Electrons turned out not to be so much just like particles, but also like waves. And we learned that through the double slit experiment, where we had these two slits. Here's the electron gun, and these electrons were shot out.
Oh, yeah.
And they were somehow, they interfered with each other like waves interfere with each other. There's some points where there was constructive interference and some points where it was destructive interference. It shows up like this. This is where the electrons hit. And it's strange because they acted like waves there. Really weird stuff. Really weird stuff. So these electrons behave like waves. So Schrödinger came up with a wave equation. And that wave equation then gave us various shapes that electrons could be in. And those shapes where these electrons could be in, they look like this. They look like this is kind of a shape they can be in. You can also have a shape that looks like this. And it can be oriented in different directions. Okay? That could be on the z-axis, coming out of the board. This can be on the y. This can be on the x. Okay. Now, those are just the different axes, and these are all p subshells. Right? And you can fit in different numbers of electrons into these. So if this is an s subshell, it has this. Let's say this is the 1s orbital. We can fit in 2 electrons in there. Okay? And don't forget, this whole thing, these electrons, are situated around an atom. So the nucleus is in there. It's in there somewhere. Okay? Then, let's say that we want to fill up around the atom a little bit more, around the nucleus a little bit more. So we put our next set of electrons into the 2s orbital. There's only one orbital, so let's put them right there. I drew them right next to each other. We could draw them over there if you'd like to. It's just, this is the shape where they're likely to show up. But we can fit 2 electrons in there.
Battery.
Okay, battery's low. Oh my gosh. Now each one of these p orbitals you can fit in 2. Like this. But you have to fill them up in a certain order, and I've ordered them wrong. So the first thing you do is you put 1 p electron in each of these orbitals, and then you can fill up the rest. That's the order you can do it in. Right? If you're looking at this chart in terms of energy, how we're filling these things up, at first we're filling up the 1s. Then we're going up to the 2s, then the 2p. So if I want to describe this with a chart over here showing the energies that these electrons are taking, we can do this. We can say first we put the electrons in the first orbital, then we go into this 2s orbital, and then we're going to fill up each one of these p orbitals, these 2p orbitals, and then we'll fill them up completely right there. Okay? Alright. Pretty cool, huh? Let me turn on the lights. Ah! Okay, so then after that, we of course got this 3s, and I just know this off the top of my head, but if you did not know this off the top of your head, that's okay, because you're given the Aufbau. The Aufbauprinzip. And this Aufbauprinzip looks like this, and you'll get this on the test. Don't worry, you're going to get it. This will describe every single atom in the periodic table. Alright? So then we have the 2p over here, then we have the 3p, then we have the 4p, it's p, that's 5p, 6p if we need it, I think we do.
Don't worry.
Oh my goodness. Then we got the, then we got the 3d, then we got the 4d, then we got the 5d, then we got, oh my gosh, let's just do the 4f and then the 5f. I think we're going to need 6d maybe, I don't know, 7p. Alright, now the Aufbau says this is the way that you fill up the energy levels of electrons.
For the next topic, the Geiger counter, you only need to know how it works, right? Like the ionizing radiation splits an electron and that releases a positive or negative charge, right?
Yeah, so the Geiger counter, let's do that. Sorry, I'm doing this. I have a lot of information I just want to go through. Now, let's do that real quickly. Geiger counter, and then we'll call it a day.
Cool.
Alright? The Geiger counter works something like this. Here's a Geiger counter. Okay, in the middle there's this. So on both sides of the Geiger counter we've got something like this. So let's say that this is a negative charge on both sides, very high charged wall over here, and we've got a highly charged center beam, I guess you call that? I'm not sure. So this is like cutting open the Geiger counter. Okay. Let's say that we get some ionizing radiation coming in. Here it is. Maybe this ionizing radiation is something like, I don't know, like UV light, something like that. So inside here we've got a whole bunch of gas atoms. Bunch of gas atoms. Okay? They're just hanging out. I'm not going to draw all of them because you could draw them everywhere. I'm making them very, very large and out of scale to show you this point right here. If you zoom up on this little section right here, zoom up on that little section. So this is the same box, just drawn bigger. You've got these little atoms right alongside this ionizing radiation. There it goes, it's coming up, like that. And these atoms, if you zoom up even closer, you can see, oh, there's the nucleus, and then you've got these electrons on the outside. Maybe this ionizing radiation comes along and does something mean. Maybe it goes over here and it rips away an electron. We took it away, so now this electron goes flying off into the sunset. Okay? So that makes this atom charged, since we took away one of its electrons. Right? So now this is a positively charged atom. So this whole atom right here is now going to be attracted. It's going to be attracted to the negative side of this Geiger counter.
So once the radiation splits the electron, the atom is what makes that positive or negative charge.
Yes.
That's okay.
So now that ion is attracted to the wall over there, and maybe an electron gets picked up by another atom and makes that other atom into an ion as well, maybe a negatively charged ion, and then that is attracted to the positive side. So when you have these ions, when they're attracted, they go towards this wall. They create this electrical current inside the Geiger counter, which creates the click that you hear.
Alright.
Okay? Eventually it leads to the click. So that's that. That's the Geiger counter. And alpha, beta, gamma radiation, you know all about that. All that's